Benvenuti a tutti. Welcome everyone. Are you guys enjoying scala-italy? Very good. So let's start by asking, who has compiling time of less of 1 minute in Scala? And compiling test files as well. Okay. Couple people, all right. Who has less than 5 minutes? Okay, less than 10 minutes? Yeah, what about the other guys? There's still a few ones that they didn't leave their end. All right, so yes, triple quad is me and Julian Dragos. As Gabriele said, Julian couldn't make it, unfortunately, but he sends you all his greetings. So our story, well, we were working together at Lightman TypeSafe. Actually, before that, we worked together at Scala Solutions. So the company that was created, well, together with Scalable Solutions, they created TypeSafe, and then that became Lightman. And we started our story by working together on the Scala IDE for Eclipse, and then we've been working on a couple of other open source projects. In this case, we were working on different teams, but at some point we decided that, well, we all love Scala, and we're really in love with Scala, so we wanted to do something good for the Scala community. And what was the number one problem that we were hearing from everyone was like, well, Scala, we love Scala, but it takes too long to compile. And so we decided to do something about it. And our mission at Triple Quad is to cut down on Schwartz fight due to long Scala compile times. So maybe you can relate to this feeling. We love Scala. We feel it makes us so much productive, but are we? Right? Like sometimes it just takes too long to compile. So what can we do about it? Well, on one side we could go and write sophisticated technology to pull us back to work when compilation is done, right? So that whenever we need to be over with our checking the Twitter feeds or what happened on Facebook, we can get back to work. But context switching is extremely expensive, and so the longer it takes to compile, the less productive you feel you'll end up being. So today, I want to talk a little bit about the state of Scala releases, kind of understanding, is Scala getting any faster? Do we know? Then we'll spend some time looking at how to investigate long compile times, what you can do today to detect and fix those things. And last but not least, the free lunch, which boils down to use triple quad Hydra. So Scala releases. Well, Scala 2.12 was released in November 2016. And the one thing that we got from it was a complete new rewrite of the backend to take full advantage of the Java 8 runtime features. So there is a new encoding for traits, and there is also a new encoding for Scala lambdas. And that basically, to us, what it means is that the footprint of the binary was drastically reduced because we don't need to generate all those classes that were, it was the case before Scala 2.12. So we're taking full advantage of the Java 8 goodnesses at runtime. But what about performance when compiling Scala code? So, well, what we can say is that, for instance, shapeless, I talked to Miles, I think it was back in November, and he said that, well, for him, Scala 2.12.1 was actually being 20% slower in compiling his test than 2.11.8. So he noticed a slowdown. But if you talk to the Scala team, they're actually extremely enthusiastic about Scala 2.12. In their benchmarks, it seems that compilation is, I'd say, comparable or maybe even slightly improved. So what we can get from this is not a lot, but what we can say is that it's hard to assess if compilation speed is actually getting any faster in Scala. And the good news is that the Scala team is working on this. They're working on automatizing the process of, can we know if we are regressing by committing this code? And that will also, give them the power to go back in history and check if there was any commit in previous history that actually brought a drastic compile time and inefficiency to the code base. So we will get better compilation, single-threaded compilation. But, so are we good? We don't have to worry about this problem because the Scala team will do it for us? What do you guys think? We're good, like they do it. They take care of their things, so we don't have to do anything on our side. Of course not. we can still do plenty of bad things in our code, right? We can write macros that maybe they trigger type checking, and maybe they call other macros, and this process can just go and on and on and on. And in fact, what seems to be an innocuous source file, it actually ends up being maybe 45. Like we've seen this. Like you were looking at some source file, it was like 200 lines of code, and then actually you were looking at how it was expanded, and it turned out it was 45,000 lines of code. Because of macros that were being triggered during compilation. So what can we do today to detect and fix those inefficiencies that we may have in our code base? Well, I'd say we have to know what are the existing tools, and we need to take advantage of them. And so this is what I'm going to be covering in this initial part. So the Scala compiler offers you lots of compiler options. Here I've listed a few ones that I would say are no-brainers, and they basically detect unused code. So things that you're basically not using, they might just be slowing up your compile time. So if you don't want, of course, every of those flags has an overhead. In general, these initial ones is extremely low, the overhead. But again, if you don't want to pay the overhead, maybe at every time you compile, you can still put them on your CI. At least that way you know if there is something that isn't working well as expected, you can just fix the problem then on your machine. Those for me are sort of low-hanging fruits that you can easily go and catch for yourself. But usually you're not going to get 20% faster compilation just by enabling those flags. So if you want to achieve those, well, if you actually want to detect those inefficiencies, you'll have to be ready to go and explore basically how deep the rabbit hole goes. So what are these other flags that can help you? Well, the first one is minus verbose. Minus verbose is tremendously verbose. But there is one bit that is interesting. It tells you how much time it takes to compile for every phase. Basically gives you the time by phase that it takes for compiling your code. So as you might know, the Scala compiler runs your code through many phases, through many transformations. There are actually 24 of those transformations in the Scala compiler. And minus verbose will tell you each transformation, how much time did it take. So that's interesting, and we'll see what kind of information you can get in the next slide. Another one that is useful is this minus x print, and then you pass the phase. So what that gives you is the AST, so the abstract syntax tree, so the representation of your source file as seen by the compiler after the given phase. And we'll see that usually the phase that you're interested in looking at is typer. But anyway, if you don't know what are the phases of the Scala compiler, you can just use minus x show phases, and that will list you all the phases with the name. And then you can do a minus x print the name of the phase, and that will show you the AST after that phase. Then there is another one that is minus x log implicits, and that gives you a trace of what are the implicits that the Scala compiler attempt to use for inning your code, but they were not applicable. So you basically can see how many implicits were tested without success. Of course, the more implicits were attempted, the longer it will take for your code to compile. And if you have macros in your code, minus y macro debug light and minus y macro debug verbose will give you information about macro expansions, so what's happening during macro expansion. Of course, there are other flags, but in my experience, those have been the most useful to detect compile time inefficiencies. So, okay, let's say you want to get a feeling of what are your compile time. Do you have any inefficiency? I'd say start by using minus verbose, and then you'll have to do some grep to just identify how much time it takes for every phase to compile in your project. But then you can build a nice chart, and you can see something like this. So what is the chance to the eye to you? Like here we're just comparing. Blue is the akka actor module, while the green line is a project that at Zalando that we've been working with at Zalando. So it's called Teambox. We've been doing some consulting with them. I'll tell you more about it later. But there is probably one thing that jumps to the eye. So there is one big green line at some point, and that's a compiler phase. And can you guess what phase that could be? John, is not for you? It is typer. So that phase is basically type checking your source file. And as you can see, type checking is taking 32 seconds out of the 55 seconds of the old compile time. So it's actually taking more than 50% of your compile time. So whenever typer takes more than 50%, but I would say even 40%, you probably want to know why. So if you know why it's taking so much, fine. But if you don't know or you have a doubt, I think that's your opportunity to go investigate, and maybe you're going to actually find something interesting that can help you bring down compile times in your project. So I'd say usually typer should be around 30%. That's a normal number. If it's more, I think you should know what's happening. So, investigating. Usual suspects for long compile times are macro expansions. Those are an easy one, just because, of course, the more macro expansions and the more type checking that happens on these macros, the longer it will take for your code to compile. Another one, they're implicits. Again, the more implicits the compiler is attempting to, well, the longer it takes, of course. And also type inference can play a role, even though I haven't seen yet an instance where that was actually bringing down performance considerably. There was actually a tweet recently where someone said that by putting the type explicitly in the members, it was someone in the IntelliJ code base, they basically got a 17% speed up just by making types explicit. So let's say that we go into this journey of attempting to find inefficiencies. So what should you do? Well, the first thing, you should have a guess for what are the source files that are taking the most to compile. And the bad news about it is that there is no tool at the moment that can help you with that. So you need to have a guess. You need to have a sort of a sense, this file may be taking long to compile. And then what you can do is actually proving if you're right or wrong. And to prove that, you can compile that single file without anything else. You just basically add to your Scala-C options, you add the target folder in the class path, and you compile that single source file, and you see how much time it takes. Let's say that you expect it to take, I don't know, maybe, be super fast, and then suddenly you see that it takes 15 seconds. Well, you probably wanna go and dig why it's the case. And again, I've seen code base with like 30 lines of code, and then they were taking 15 seconds to compile. And again, what happens? Well, usually it's related to macros. At least that is, again, in my experience. Usually there are complex macros, and that takes a lot of time. So what do you do when you identify the source file that may contain some inefficiency? Well, the next step is that you want to print the AST after typer. Again, it's after typer because all type checking has been done. So all macro expansions or implicits have been resolved. So you can actually see what your source file looks like after type checking. And if you started with 20 lines of code and then you suddenly see, 45,000 lines of code, well, yeah, you know why it's taking so long. And so the next step would be, okay, is the code that is generated correct? For instance, it happened that in a source file, it was regenerating implicit values through macros, and it was doing that despite the fact that there was an implicit that could fit well, and there was no need to recreate that implicit value through macros. But the problem is that there was some scoping problem, and we'll look into implicit resolution and scoping soon, that was basically forcing the compiler to recreate the value through by calling the macros instead of using the one that was cached. So by identifying that problem, well, compilation went down that source file from 15 seconds to maybe 300 milliseconds. And of course, when you find something like that, you can easily share that information across the other source files that sometimes happen to have exactly the same problem. And so suddenly, you maybe get like 40% compile speed up for free. And so after typer, if you print the AST after typer, you get all these informations. If you don't see anything in the AST, anything that kind of jumps to your eye, then probably the reason for the long compile is the implicits lookup. And so you want to use minus x log implicits to actually get a trace of which one were the implicits that were attempted. And so is there any way that we can reduce the number of implicits in the scope so the compiler can actually get faster at finding the one that, well, it should use? So we're talking about implicit resolution, right? Who knows how the compiler does it? Just raise your hand. If you think you know it. Yes. Okay, good. Well, it is tricky. It is tricky. It's pretty, I mean, it's extremely bright, and I think every Scala developer should know how, at least have an intuition of how this compiler, how the Scala compiler does implicit resolution, because that will help you exactly in these cases to avoid bringing in the scope the wrong implicit. So, how do you get to know about the implicit resolution algorithm? Well, there is the Scala reference. There is chapter 7, 7.2, I believe. And that gives you the explanation for implicit resolution, how it's done in the Scala compiler. Right? And actually, the Scala reference is very readable. I would highly encourage you to go and have a look on your own. There are really like almost no Greek letters. It's not like only PhD or student can understand what's in there. It's really made for engineers like us. So I definitely encourage you to go have a look, and I think you'll find it very readable. But okay, let's try to build an intuition of how implicit resolution works. So we have this example, which I would definitely not encourage you to do in your code base. We have a show method with the signature. It accepts a map as a parameter, right? And what we're passing to it is an employee. So of course, this code will not type check. To type check, well, the compiler has to find an implicit so that it can transform employee into a map of ID employee, right? It's a stupid example, but just to make a case of how implicit resolution works. So the first thing that the compiler will do, what is it? Like, what is the first thing that you believe it will be doing? True, okay, but like, before that, yeah, I didn't want to code that before that. I mean, it would just look in the current scope. Is there an implicit in the scope that I can use to transform an employee into a map of ID employees, right? So that's exactly what's happening as a first step. I'll just look in my scope and see maybe there is an implicit that is imported that I can use to heal that expression. If I can find one, I'll use it. And I'll move on, right? That's the first step. That is the easy step, I would say. What happens if we cannot find an implicit in the scope that can help the compiler healing that expression? Well, then it will start looking into this thing that is called the implicit scope. So what is the implicit scope in the example that we were looking at before? Well, we had this show method that was taking a map of ID and employee, right? So the implicit scope will basically be built by looking at the companion object of map, ID, and employee. So companion objects always play a super important role with implicit resolution. So we always look at a companion object of those types, in this case map, ID, and employee, and see if we can find an implicit that can help us heal the expression that is not type checking. But we're not just going to stop at that. If we cannot find an implicit, then we're actually going to look into the classes that map extends. So map is a compound type. It extends seek, iterable, and others. So we're going to be looking into their companion objects, and so on. So it's a recursive algorithm. And you can see that the more classes you have, the more objects you have, and potentially the more implicits you have. So you have all the implicits in the current scope, and then you also have all these other implicits that are in the companion object that the compiler will have to look at. So just imagine how many implicits that you have your program, and how many times Scala implicit resolution is kicking in, and how costly that can be eventually if you have so many implicits that you're looking for. So the takeaway for implicits is that you should try to limit the implicits that are in the scope. So the scope was, well, the first thing that the compiler is going to look at. So things that they're just available without any prefix, not the implicit scope, just the current scope, I would say. So what do you do to limit the number of implicits in the scope? Well, you want to avoid having wildcard imports, because you cannot control what you are importing through a wildcard. Maybe today you're not importing any implicit, but then tomorrow I'm adding a new package object, and in that package object I'm actually adding some implicit, and then suddenly all those implicits are available to everyone, right? If I'm importing, let's say, some package dot underscore. So just avoid having wildcard implicits. That way you know that you're not bringing in new implicits in the scope. And another one that you should avoid is actually defining implicits in the package object, because again, if you define them in the package object, they're available to all classes in the same package, even if you don't import them, right? So avoid that. Try to reduce the number of implicits that are in the scope. So where should you put your implicits? Always try to put them in the implicit scope, because in the implicit scope, the compiler will only look at the implicit scope if it's needed. Maybe it's not needed, or maybe it's looking for, let's say, employee, and you have some scope, some implicits in the scope of, I don't know, data. It's not going to go into data companion object to look for easy implicits. It's only going to go into the employee object. So by put implicits in the companion object, you're just limiting the amount of work that the compiler will do. So, and in fact, when we were working at this project at Zalando, simply by moving implicits that were defined in the package object, by moving them into the implicit scope, that yielded a 40% compile time reduction. That was it. Like, you just, like, they literally didn't change anything. And they got 40% time speed up. They were very happy. So, in fact, we actually also wrote an article together with Eric Torrebore. He works at Zalando. And so if you're interested in understanding more about the work we have done there, have a look at that, at the article. So what about macros? Well, macros are fantastic. They can reduce boilerplate, right? But macros can also be responsible for 80–90% of your type checking time. It really depends. I cannot tell you, I cannot give you the whole truth, but they can be responsible for that amount of time. So I think for me the takeaway is that you need to be practical about using macros. So are they pulling their weight? Is the boilerplate you're saving, is it worth the additional compile time that you're actually inflicting to your whole team? If it is, go for it. If it's not, then I'd say you're probably better off writing a bit of boilerplate code on your own and just compiling much faster. So, yes, identifying compile time inefficiencies, it's easy, isn't it? Yeah, it's tricky. You can do it, but it's definitely not something you would want to do every week, just because it takes time. And that's why we have Hydra. That's why we created triple quote. It's exactly to solve this problem together with just making you compiling faster. So with Hydra, we have 3 goals. On the one side, we want to build a distributed compiler so that we can take advantage of, compiling on different machines. So we can just scale. We can scale up your compilation, we can scale it out, and we can just making you compiling a lot faster. But that's not it. We also want to make it insightful. So all those things that I told you about before, all those things that I was telling you should do, well, actually with Hydra, you won't need to do it. The tool will do it for you. And it will actually tell you what are the problems. And even more, it will tell you if anything bad is happening. Let's say that you're pushing a pull request, and then suddenly that pull request is causing some slowdown when you're compiling. Well, you don't want to merge the pull request, and Hydra will help you exactly achieving this goal. And the last bit is that we want it to be transparent. So it should basically integrate smoothly with your development environment. It should pick exactly where you are. You shouldn't need to change anything in your build. You shouldn't change anything your code habits, it should just work. So, I mean, distributing is pretty natural, right? Everyone thought about, yeah, I mean, should be easy to distribute compilation. Well, there are some challenges with distributing compilation. One is one problem is that you may end up having some source file that depends on each other, but they're being assigned to different workers. So this is a challenging aspect that we need to deal with. And well, and the second one is that building a distributed system is not simple. And yeah, you've been hearing about it. Probably you're doing it yourself. So it is a tricky problem. So if we take on this journey, let's try to think what are the maximum speedups that we can achieve. Well, Amdahl's law can help us with that. So basically, we can tell what is the theoretical maximum speedup we can get by distributing. So P is the percentage of parallelizable work. Ideally, it should be close to 1 or 1. And S is the speed up that we can obtain for parallelization. So in our case, is the number of cores that we have available. So as you can see, if S, let's say, tend to infinite or is big enough, then this equation is completely determined by the value of P. So it completely depends on how much work is entirely parallelizable. So let's try to make some numbers there. Let's say that the non-parallel work is 50%. Well, that means that our maximum theoretical speedup that we can obtain is 2 times faster compilation. If we can increase the amount of work that we can do in parallel, let's say we bring it to 40%, then we can go up to 2.5, and so on. So if we bring it to 10%, in theory, we can go up to 10 times faster Scala compilation. Wouldn't that be great? So what is this non-parallelizable aspect? Well, it's basically a constant factor that we just have to pay. There are things that we cannot change, like just-in-time compilation will happen on every thread if we're compiling on parallel. So there isn't much we can do about that. There is some memory bus contention that will happen just because we're consuming more memory by having more threads. And there is also some penalty due to this interfile dependency that I mentioned before. So after telling you this, yes, first let's talk about where Hydra is today, and then I'll show you some numbers so that you can relate to this table. So today, since building a distributed compiler, to build a distributed compiler, first we need to be able to distribute locally. It's a requirement. We need that. First, we should make full advantage of the existing machine, the existing hardware, and then we can actually scale out to the cloud. So today, Hydra is exactly that. It's a parallel Scala compiler. It can actually take full advantage of all your cores and parallelize compilation. The granularity at which it works is the compilation unit. That is the term used in the Scala compiler, but that just means a source file. So it basically takes your source file, it assigns them to different workers, and then compiles them in isolation. And we parallelize the whole pipeline. So by pipeline, I mean all these phases that I mentioned before. Well, Hydra parallelize all of them. It's not that it parallelize only 1 or 2 or 3 of them. So what are the challenges? Well, I mentioned it already that we have this problem with interfile dependencies. That, of course, it's a problem that we need to deal with. And then there is also laziness and mutability, just because we are in the Scala compiler. So if you look at the Scala compiler, well, it's mutable. It's not an immutable implementation. It is mutable. And so you need to be careful whenever there is mutability, of course. Since we're in process, we might be tempted to do sharing. But of course, we need to be careful when we're sharing mutable state. So our initial approach was to actually go for a share nothing design. The problem with that is that it doesn't really help you that much in achieving fast compilation. It only brings you that far. But then at some point, you do need to have some mutation and to have some sharing across these workers. So our approach was to actually add back sharing in a controlled way And that's actually what is making it work. That was the only way to achieve the kind of performance that I'm going to tell you about in the next slide. So here we have just a couple of projects, a couple of modules, where we're comparing the vanilla Scala and Hydra. So in the first one, we have specs2 core test, and then specs2 common main. And we see that we have a bit better than a 2 times speed up, which I think is pretty nice speed up. Those benchmark have been done on a laptop machine. This is actually an i7 2.6 gigahertz. It's not really recent. It dates from 2013. But Julian has a 2016 machine, and it's exactly the same. So they didn't change anything. They just make it consume less energy. That's where it goes. But performance-wise, it's exactly the same. And then we also tried shapeless. And one interesting aspect is that we compile shapeless core JavaScript. So we support Scala.js, of course. And in this case, the speed up, I would say, was a bit less exciting. We basically got a bit more than 30%, almost 40% speed up. But of course, we wanna get more. But actually, when we were compiling shapeless, what we were interested in wasn't really compiling shapeless, but it was getting a feeling of how projects that are using shapeless, how fast would they go with Hydra? And so we thought it would be better to compile shapeless tests, because those are representative of how the shapeless libraries will be used by people, right, in their code. So this is actually what we obtained by compiling shapeless test. And if you can't see it, if you can't tell it, that's what it means. We got a 3 times speed up on shapeless test. And we had very similar results Zalando on their Teambox project, as they are also using type-intensive libraries, shapeless being one of them, and they also got very, very good results. So this seems to be, I'd say, hopefully it is a pattern that we will see in other projects, that they use shapeless and other type-intensive libraries. So what about cold and warm and warm performance of Hydra compared to the Scala compiler? So cold performance are actually important, because when you run on Jenkins, you get a cold JVM, right? So if you can bring that down, it means that the feedback loop is getting faster. So you're actually telling your team, and you're actually multiplying that feedback loop, because it's not only telling you, the developer, or a single developer, but it's also telling the whole team how your pull request did. So what we can see is that we did basically 5 runs, first with Scala 2.12.1, and then with Hydra. This, again, was on the Teambox project. And we can see that the cold compile is actually, for Hydra, the cold compile is faster than the warm compile with the Scala compiler, with the vanilla Scala compiler. So I think that's impressive. And the other thing you can see, is that compile times went down when you have a warm JVM. They went down from something like 65 seconds down to 25 or 26 seconds. So again, it was almost 3 times faster, just by using Hydra. They really didn't have to change anything. You just add this plugin, and then we take care of the heavy lifting. So the triple quad Hydra compiler is a drop-in replacement for Scala C. Today, it is a fork, but we're actually hoping to not making it a fork. It's something we are working on. I think the way you should think of it is that it's a tool for productivity. That's what we aim at being. We don't want to be a fork. It's not our intention. It was only the fastest way to get there, to get to a tool that you guys could use. But we have really no intention to be a fork. And in fact, one of the things that we're aiming at is that, actually, one thing that we guarantee you is that the binary produced by Hydra is the same. So it's not binary compatible. It's the same as the one produced by the vanilla Scala compiler, so that you know that you can, you can run it in production with confidence if you want. And we currently support 2.11.8 and later, and 2.12.1 and later. Support for other Scala versions are, of course, possible, and it will depend just based on demand. And again, other forks should work too. So in this case, I'm thinking about the type level compiler. On our side, by unforking, we will make working with the type level compiler much easier. But also, if there is demand to work for Hydra to work with the type level compiler, we can also just do it at the moment. So that really will depend on demand. And last but not least, at the moment we have an SBT plugin and also a command line option, or yeah, we have also a command line option. And of course, we plan to have other integration with other building tools like Maven and also IntelliJ. That's also something in the making. Good. So what about the insights? This is what we're working on right now. Is giving you visibility on what happens. We want to collect metrics because on the one side they're going to help the tool, but on the other side they're also going to help you understanding what's going on, so that you can detect inefficiency, and you can also prevent inefficiencies from being committed ever to your code base. Those are just a few examples of metrics that we're going to be collecting, but of course there's going to be more. And if you have ideas, just send us to us. If there is something you'd like to see, we'd be happy to hear about it. So how do you use Hydra today? Well, that's all you need to do. It's really just one line. You add the plugin, and that's it. You don't have to change anything else in your build. If you like it, you keep using it. If you don't like it, you take away that line. It means that it's extremely easy to try it out, and it's really easy, to just remove it if at any point something doesn't work. It's a risk-free thing to do, basically. And yes, as I mentioned, Gradle and Maven support will come based on demand. And we already have some, I'd say, some potential customer that would like to see integration with Maven. So yes, Hydra is not open source. It's subscription-based. But so how are we giving back to the community? Well, of course, there are things that we are identifying in the vanilla Scala compiler and that we're pushing upstream. Like recently, Julian has identified a problem with the class handling in Scala 2.11, I believe, but also actually it's in Scala 2.12. And he just opened a ticket and is working on a fix to make it faster. And the reason is just that he also will make us faster. So there is no reason for not sharing with the rest of the community. Of course, there are some things that we cannot share, but also because they don't make sense for the vanilla Scala compiler. The Scala team will not want to maintain things that they're completely related to how the tool works in the parallel setup. So that's how it's working out, basically, the relation between us, triple quote, and Scala and the Scala community. Another thing that we're doing is we're implementing C25, which is going to add static to the language. So there are ways through which we're giving back to the community. So about the roadmap, today until end of Q3, we have a private rollout. So we're engaging with organizations that they're feeling the pain of long Scala compile times. So if you're one of them, we would definitely like to hear. We'd be happy to collaborate. And at the same time, we're building these insights and metrics I told you about, so that you don't have to do all the work that I covered in the first part of my presentation. And then in Q4, we'll have general availability. So it means that individuals, like any developer on Earth, can just go, download Hydra, try it out, see if he likes it, and then from there anything can happen, I guess. And in Q4, we'll also start working on building Hydra in the cloud. So it will be available both as a service, but also on premise. So those are our plans. And again, if there is anything that you'd like to see, just tell us. We'd be happy to hear your feedback. If there is anything we didn't think about and that you feel painful related to build times, just let us know, and we'll see if we can do something about it. Thanks, everyone. I'd say as a next step, again, I would highly encourage you to have a look at this article about Hydra. And it's actually about Hydra and also about the consulting work that we've been doing together with Zalando. Again, if that's something of interest for you, just drop us a note at ping@triplequote.com. Thanks, everyone, for the attention.